Threads allow us to build programs where parts of the program can run independently of one another. Threads can, big emphasis on can, help you make faster and more responsive programs. For example, as a web developer, I'd like the server framework I'm using to start responding to the next request before it's finished responding to the previous request. As a game developer, I'd like my game engine to capture player inputs without being blocked by the renderer. As a data engineer, I'd like to process large sets of data with parallelism. This series is accompanied by a free book. Check the description for a link straight to this chapter. My name is Daniel. Welcome to Iris. We're going to step through how we can run code in a thread, including sending data before it starts, how we can wait for a thread to end, including receiving data when it ends, how we can communicate with running threads, and how we can share state between threads. We'll also be touching again on our marker traits, send and sync. Before we get into the rust, it's worth discussing what a thread actually is. When you run a program, that specific instance of the program is called a process. The process incorporates not just the instructions to be run, but is an abstraction around various resources that the program has access to, such as memory. You can run multiple processes which the operating system will schedule separately, which could allow you to do more things at once. However, those processes won't, or at least shouldn't, have access to the same memory. There are ways to communicate between processes, but they can be slower and more restrictive than if we could just share memory. The specific part of the process responsible for executing code is called a thread, and a single process will always have at least one thread, but can have many. Threads are also scheduled by the operating system independently, allowing one process to do multiple things effectively concurrently. Your program always has at least one thread. Even your basic Hello World program runs in a thread. What we're interested in today, though, is how do we start more threads? This is a process called spawning. To spawn a thread, we use stud thread spawn, but this will do little on its own. If we run this code, can you see what's missing in the output? It looks like our thread didn't run, but actually, it's even worse than that. When writing this portion of the book, this is the output I consistently got from my Mac and from Rust Playground. That consistency actually surprised me a little bit, but when writing the script for this video on my Windows machine, I got this. This is the actual inconsistency that I was expecting. It's not that our thread doesn't run, it's that we don't know if or how much of it will run. Spawning a thread returns a join handle. The join handle is what ties the spawn thread to the thread that spawned it. If the join handle is dropped, which in the previous case happened instantly, the thread is orphaned. It may still run, but in that case the process ended at the end of main, so whether the child thread ran or not was no longer up to us. We can tell the main thread to pause and wait for a running thread to end by calling join on the join handle. We've been using closures, but functions work just as well and can be better for more complex programs. The only restrictions are the function needs to be fn once returning t, send and static, and t also needs to be send and static. Exactly when threads are allowed to execute code is controlled by a scheduler, which we can't directly manage ourselves, but we can influence it. Putting one thread to sleep could allow another thread to run. If we run this code as is, you'll see the main thread runs to completion before the child thread even starts. If we put each thread to sleep after it writes to standard out, we can encourage the scheduler to start working on the other thread if it isn't already. There's two very important things I want you to note here though. Firstly, thread sleep is not a timer. Your thread may sleep for longer than you requested or not at all in certain situations. Secondly, the scheduler ultimately decides when code is run, so there's no guarantee you will get this exact output. So bear that in mind if when your code runs matters to you. So now that we can run threads, let's start looking at how to send data back and forth between them. We can pass data into a thread before it starts, so long as the data is send. We previously talked about this trait in the traits video, but to recap, data is send so long as it can be safely sent between threads. This trait is automatically implemented for all types that can be send, though it is possible to opt out of it if you need to. We can move data into the closure that will be sent to the thread using the move keyword. Here, we move the entire data vector into the spawned thread. You can also return data via the join handler. This means you could pass hard work to a thread and do other work before coming back to check on the thread at a later time. A little side note, if it's helpful, you can check if the thread is finished with is finished. Here I'm using it to let the person running the program know we're still waiting on the thread to do its work, but the program is still running. Now we can start one thread, there's no stopping us. Modern schedulers can manage a lot of threads at once. However, so far we can only send data between a child thread and the parent that started it, and only before and after the thread runs, not during. What if we want to communicate across multiple threads, or send data to a thread while it's running? Multi-producer single consumer, MPSC, is a queue pattern that allows us to create channels with multiple senders that can send messages to a single receiver. As per the name multi-producer, you can clone senders, but each of those clones can only send to that one receiver. The sender and receiver types are send, that means that you can create them in one thread and send them to another. Let's create a bunch of threads and give each of them a sender that points back to a single receiver. We moved the sender into the closure being run in the map method of an iterator. Because the closure now owns it, we can clone it here and move each clone to the thread we're spawning. We'll send the receiver to a final thread that will collect the data from the other threads. Finally, we'll join all the threads with a sender before we join the thread with the receiver. This is important because this is the first bit of code we've produced that can cause a deadlock, where two or more threads get blocked by each other. If you forget to join the senders first, they won't send their messages but will block the receiver thread here, so your program gets stuck. For what it's worth, there's no built-in channel type with clonable receivers. However, there's nothing stopping you building your own type for that. Or, a potentially better option, there are crates that already support it, like Crossbeam. So we can send messages across threads, but what if we need multiple threads to have access to the same data, maybe even able to edit that data? To do this, we need to use types that implement the sync trait. Something is send if it can be sent between threads, but doing this moves ownership from one thread to another. Something is sync if a reference to it can be sent between threads. So T is sync if a reference to T is send. Most things are sync, but we still have to abide the rules of references in that we can have as many immutable references to something as we like, but we can only have one mutable reference. Furthermore, references cannot outlive the data they reference, which is a little harder to confirm with threads. How do you know the thread referencing your data doesn't exist for longer than the data it referenced? One option is using scoped threads, which we can create with stud thread scope. The scope function takes a closure with a single parameter that gives us the scope context. We can use the scope context to spawn threads. We don't need to keep track of join handles this time. All scoped threads are joined at the end of the scope closure. However, the spawn method on the scope context does still return a join handle if you want to handle potential thread panics, which you probably should do. The scope function blocks the thread that called it until all the threads it started have been joined, so after that we're safe to modify the data again, which here would require a mutable reference. You can also send mutable references across threads like this, but bear in mind only one thread can access the mutable reference and it must end before we can access our data again. So we can share readable data across multiple threads or share writable data with a single thread, but what if we want to share read-write access to data across multiple threads? Let's start by thinking why we can't do this with just references. When we're using threads, multiple parts of our program can be executed at the same time. Imagine we have two threads that want to change the data behind a reference based on what is currently stored there. Something simple like each thread wants to multiply a numeric value. It could be that at runtime, code gets executed in the following order. Thread 1 reads the value from memory into a register, thread 2 reads the value from memory into a register. Thread 1 multiplies the data and stores it back in memory, thread 2 multiplies the data and stores it back in memory. In this situation, we've lost the effect of thread 1, which could be a bug. Let's consider a more serious version of this. Imagine the data, rather than being a single value, is an image stored in an array-like structure, and you're applying multiple processes to the image at the same time. This time, if one thread were to override another's work, we have a much more obvious problem. To get around this, we need to prevent two threads accessing the same piece of data at the same time. There's a general software abstraction concept called a mutex that makes access to data mutually exclusive. Rust provides its mutex through stud sync mutex. Once you place data inside a mutex, to access it again, you need to lock the mutex. If the mutex is already locked, then the thread currently trying to access the data needs to wait for the existing lock to be released. The lock method on a mutex returns a result containing a mutex guard. When the mutex guard goes out of scope, the lock is dropped, allowing other threads to access the mutex. If the thread panics while holding the mutex guard, that poisons the mutex, which is why lock returns a result. However, there's still a slight problem here. We're currently very dependent on using scoped threads because we need our references to point back to the owned data, but scoped threads aren't the norm. In fact, most of the time you use threads in Rust, they will probably be abstracted behind some other framework, for example, a web server, a game engine, or data processing tools. The problem, of course, is that we don't know when the owned data will go out of scope and no longer be accessible. We can solve this problem using an atomic reference count. We haven't discussed reference counting yet, as it's usually fairly niche. However, reference counting allows you to share data around an application without needing to clone it and sidestepping complex reference rules and lifetimes. It works by moving the data you want to share onto the heap and allowing access through a reference count type. When you clone the reference count type, instead of the data being cloned, it modifies its internal count of how many clones exist. Every time a reference count type goes out of scope, the count is decreased. Once the count hits 0, there are no further references to the data, and so it can be safely dropped. Now, if you've paid attention as to why we need a mutex for modifying data across threads, you'll see that using a normal reference count won't work. If the reference counter is being cloned or dropped while also being cloned or dropped in another thread, you could end up with an inconsistent count of references, meaning data gets dropped at the wrong time. This is why we need a special reference count type, stud sync arc, an atomic reference count. Atomic data types guarantee atomic changes. Atomic changes are guaranteed to appear to be instantaneous to all external observers, meaning that two threads can change a value, but these changes cannot overlap. Arc is a little slower than Rust's built-in basic reference counting type, stud RC, but prevents corruption across threads. Just a quick side note, I don't think I've ever used RC, but I use Arc all the time, so don't worry that we didn't cover it in this series. If you need to pass data around in a single thread wrapped in its own container, it's there for you to use. So, armed with this knowledge, we can go back to unscoped threads. Like earlier, we can clone the arc in the map method of the iterator and move the cloned value to the thread. Arc also implements deref for its internal type, so we can call lock on the mutex from the arc. And that's it. Hopefully threads feel a lot more accessible now, but let me know in the comments if you have any questions or want to share tips, tricks, or things I've missed. First, if you've enjoyed the video, remember to like and subscribe. And once again, a massive thank you to my Patreons at all levels. You folk are amazing. Now, I've changed the order of the last 3 videos. Async Rust is now going to be the final boss of Iris, using a lot of what we've already learned. Instead of async then, the next video will be on macros, specifically macro rules, which is a built-in tool that allows metaprogramming in Rust. Macros are great to mitigate lots of repeated boilerplate code, can be used to create domain-specific languages, DSLs, and I'll be showing off my specific recent use case. This comes from the app I'm building on stream, which I don't think I've mentioned on the Iris videos yet. We're building a job tracking app, and the stream's chat has been filled with really wonderful people with amazing thoughts and ideas and encouragement. If that interests you, do drop by and say hi here on Tuesdays at 7 PM UK time. So, whether on stream or in the Macros Iris video, I'll see you next time.